So this is just part two. This I'm gonna start off with the rest of the Hess's law, and then we're gonna move into the ideal gas laws and how you can identify one. And yep, let's go with Hess's law.
So for this Hess's law worksheet, so for the next all right, so we're gonna go ahead and just do number 2 on this worksheet for Hess's law. This is the second version of Hess's law equations that you'll find, and this is basically saying that you need to find a delta H by using these separate balanced equations. But in order to get this delta H, you want this specific equation in order to get the delta H you want. So that means that we're gonna have to manipulate these 3 balanced equation and their delta H's in order to find the overall delta H. And we need to make this equal to this. So in order to do that, we're gonna have to manipulate it by flipping it or multiplying it or doing whatever we need to do in order to get this. So I'm gonna go ahead and rewrite this on a separate sheet of paper so it can be more easier to follow. So this is the overall equation that we want, and these are our given balanced equations. Here, let me fix this H, it's bothering me. All right, there you go, it's ugly still. All right, so starting off, I can already see what we can change to get the equation that we want. So first things first, I would want to fix this. I want to get this 4 NH3, and there's only one NH3 here, which is right here. So this is on the product side, but we want it on the reactant side. So in order to change this to the reactant side, we're gonna have to flip it, meaning that the products are actually gonna turn into the reactants, and the reactants are gonna turn into the products. This is gonna cause the delta H to change as well, but only by its sign. So since we flipped it, the delta H is going to be positive 91.8. So we're gonna go ahead and scratch this off because it's no longer true according to us. And that equation is really going to be 2NH3 yields N2 and plus 3H2. All right, so that's our new equation since we flipped it, because we need this NH3 on the reactant side because our overall equation is asking us to. Because we flipped it, it also changed our delta H by making it into a positive number. But it's not satisfied yet because it needs to be 4 NH3. So in order to make this a 4, we're gonna have to multiply the whole equation by 2. So multiply by 2, making this 4, making this 2, making this 9. All right. And the delta H is going to be affected as well because it's going to get multiplied by 2 as well. And I'll go ahead and do that later because mental math is not with me right now. All right, so now we're just going to rewrite it again because it's sloppy. And now our equation is going to be asking, now we have this right here. Yields 2N2 plus 9H3H2. All right, so that's our new equation since we manipulated it twice. All right, so now we've satisfied the NH3 in our equation, but now we also have to satisfy the rest of these. So from the looks of it, I can automatically tell that this NO2 needs to be 4NO. And once again, in order to get 2, we're just going to have to multiply the whole equation by 2. So we're going to do it by 2. This turns into 2. The O2 turns into 2. And this right here will turn into 4. And then the delta H would also be affected because it'll need to be multiplied by 2 as well with the negative. You don't need to change the sign because you didn't flip it. We flipped it here, so we needed to change the sign. And we also multiplied it by 2, so we have to also multiply it by 2, but a positive. All right, so now that 4 and 0 is satisfied, and now we need to satisfy this 6H2O. H2O is here in the bottom. We're not going to need to flip it because it's already on the product side. So now we're going to have to multiply this whole equation by 3. So I do that, multiply by 3. This turns into a 9. This turns into a 3. And this turns into a 6. So we satisfied the equation, but we're gonna also have to multiply this by 3. All right, so now I'm gonna go rewrite everything so it's clean and new. This is how our 3 equations looking like after we manipulated it, but I still haven't touched the delta H yet, so I want to do that at the end. But I kept everything the same. I made sure it was exactly the same here. So now since we manipulated it and made it to where we get what we want, now we have to cross out repeating variables. Well, not variables, rather elements or compounds. So in this case, there's going to be a 2N2 on the reactant side and 2N2 on the product side here. So these are going to cross out. All right. There is 9 H2s on this side and 9 H2s on this side, so these are going to cross out as well. And here there's 3 O2s and 2 O2s, and they add up to equal the 5 O2 that we need. So our final reaction is going to be 4NO plus 6H2O. So this is what we're left with as our final equation, which is exactly what we need in order to get what we want. So now, in order to find our delta H, because that's what the problem's asking us about, we're just gonna have to do the math and add them all up. So we're gonna pull out this handy dandy TI-84. So we're gonna do negative 180.5. So we're gonna times that by 2, and that's gonna be that first one. Here it's going to be a positive 91.8 times 2, which is going to be equal to that. And here we have a negative 483.6 times 3, which is going to be that. So now I'm going to just write down all these numbers. And I understand it's a long process, but you know, it's always a long process. So since these are the new delta H's, obviously you can tell that they changed drastically because we manipulated the equation. So now all we have to do is just add all these up. So I'm just gonna do it at the calculator now. Here you go, add them all up, and our final delta H is gonna be a negative 1,628.2 kg, and that is going to be our delta H for this problem. And that's how you solve a simple Hess's law problem. Okay, to begin with, we have our ideal gas law equation, which is PV equals nRT. The P is going to stand for pressure. V is going to stand for volume in the reaction. The N is going to stand for moles, not grams of moles, just straight moles. R is going to be the constant, which is 8.3145, but that's for kilopascals. But for ATM, atmosphere, what we measure in, is going to be 0.8205. So what we can do with the ideal gas law is manipulate it in a way to get 3 other different type of gas laws that there also is. We have Boyle's gas law, which is PV equals K. And in that, we use pressure from the first reactant and its volume, and that equals the pressure of the second reactant and its volume as well. So it's tied into the relationship between pressure and volume, and what it means to increase pressure and what it means to decrease pressure. Because in a Boyle's reaction, an increase in pressure will cause the reaction to decrease in pressure. So it has that relationship, and a decrease in volume is going to have an increase in pressure. The volume of a fixed mass of gas varies inversely with the pressure at constant temperature. So that's its relationship between each other. It's shown like that in the graph. Our second gas law is going to be the Charles law, which is the relationship between volume and temperature. And in chemistry, we always measure in Kelvin. We don't measure in Fahrenheit or Celsius. It's always in a Kelvin scale. And in order to convert your temperature that's given, say in Celsius, all you have to do is add 273, and that would be the Kelvin degrees, and that's what you'll need to use instead of Celsius, because if you use Celsius, it will ruin your equation. So for Charles' law, the volume of a fixed mass of gas at constant pressure varies directly with the Kelvin temperature. So pretty much it always has, for identical masses of gas, it stays at a constant pressure. So, and our formula for that is going to be the V1 over T1 equals V2 over T2. And this is how it's shown in a graph. So here, what we can identify with these gas laws is that they have a relationship between a few its and bits from the actual ideal gas law, which is PV equals nRT, and from them they combine, scientists such as Boyle's, they make equations just to sum it down and make it easier for one to follow. Our third gas law is going to be the Gay-Lussac's law, which is the pressure of a fixed mass of gas at constant volume varies directly with Kelvin temperature. So it is for identical masses of gas at constant volume. And this is the relationship between pressure and temperature, and how a difference in pressure and temperature can give you a different outcome in a reaction. So the formula for the Gay-Lussac law is going to be P1 over T1 equals P2 over T2, and that's how it's shown in a graph. And for our fourth law, it's going to be the combined gas law, and that's where you can manipulate the equations from the actual gas law, because it has everything that the other three laws has. So pretty much to sum up what the combined gas law is, it's a mathematical expression of the relationship between pressure, volume, and temperature of a fixed amount of gas at a constant mass. And the combined gas laws is going to be the P1 times V1 over T1 equals P2 times V2 over T2. So it's very important to know that you can manipulate the equations to favor what type of law you need to do in a equation or a problem. So right now I'm gonna do a practice problem on PV equals nRT, how to get the missing variable, and yeah, I'll go ahead and do that right now. First practice problem for PV equals nRT. It's a very simple problem, but it's good to start simple to understand how to find what you need to do and make sure you're doing it right. So in this question for number 4, it says methane, which is CH4, is sold in a 43.8 liter tank containing 5.54 kilogram methane. Calculate the pressure inside the tank at 20 degrees Celsius. So there's two things that I can already tell that need to be changed immediately, which is So there's two things that already needs to be changed immediately. In this case, the kilograms needs to be converted to grams first, and the 20 degrees Celsius needs to be converted to Kelvin. I like doing this first before I start figuring out what pressure is, because I'll understand that I didn't make a mistake and I'm all good. So we can begin by doing that first. So I'll rewrite the question on a separate sheet of paper.
So here we wrote the question. Basically, in order to make this easier for us, like I said earlier, I definitely want to convert this kilograms to grams first, and I definitely want to change this to Kelvin degrees, so I don't make any mistakes while doing the actual equation. And that's what they often do to you, to throw you off. So we can easily convert this kilograms into regular grams by easily just what? Right up. Get it! The chingo! So we can easily convert this by multiplying the equation by 1,000. But you can easily change it by just going back 3 decimal spaces. So in the equation, there's actually going to be 5,540 grams of methane, and in this reaction, we're going to use the PV equals nRT. So this is considered as our N in the equation, but obviously it's not where it needs to be because it's still in grams. So we'll have to do some simple stoichiometry. So I understand that when you go from grams to moles, you're gonna have to divide by the molar mass of the compound. So it's 1 mole over that's 4. C is 12.01. So just to make sure we're accurate in all that we do, we'll put it on the calculator. So it's gonna be C is gonna be 12.01, and there's 4 H's, which is 1.01, so it'll be just 4.04, and it'll be divided by 1605. 05 grams per mole, and our moles for this equation is going to be, put it in the calculator, some simple stoichiometry, divided by 16.05, and there's going to be 3.45, and I'll only go 2 decimals, 3.45, 345, and 17 moles. So these are our moles. We found our moles, and next we're gonna have to change our Celsius into Kelvin, and you could easily do that by adding 273 to the equation. So we'll just put it on our calculator just to make sure everything's accurate and okay. And because my mental math isn't that well. So it's going to be 293 Kelvin. 293 Kelvin. Alright, so since now everything is in order, everything is according to the equation. Our liters is in liters and not in milliliters, so we don't have to touch that. So next, in order to keep ourselves organized, I like writing out what I have on the side. So I'd literally just rewrite the whole equation. And then we start filling them in. So pressure is unknown because the equation is asking for pressure. Calculate the pressure. So the pressure is what we want. So I'm going to put a question mark next to the P. Volume is 43.8 liters. N equals moles, and we had just calculated that by doing some stoichiometry. So it's 345.17 moles. R is our constant. In this case, we're using atmosphere since it's in moles, and we're in volume in Kelvin. So it's going to be 0.0806. And temperature is going to be 293. So since we have everything listed out now, we can easily just put our information into the formula, and well, it'll always be right because the formula is never wrong, unless we make a simple mistake like putting 5.45 in the equation, or dividing this by its molar mass and we won't get the accurate molar mass that we actually need in the equation. So let's go ahead and plug all these numbers in. So we're going to keep the P by itself since it's unknown. The volume is going to be 43.8, and that's going to be equal to moles, which is 345.17. And our R in this case, because it's atmosphere, we're going to put the constant, which is 0.0806, and our temperature, which is 293 degrees Kelvin. Make sure to always remember that it has to be in Kelvin. Alright, so we're going to bring out our handy dandy TI-84 and just plug it in. So we're going to put this side first because from now on we just have to do simple algebra. So it's 345.17 times 0.0806 times 293. And we're left off with 8151. Let's go 2 decimals in 847. Alright, and that's going to be equal to 8.34 MP. So now, in order to cancel out this 43, we're going to have to just, in order to isolate this P, we're going to have to divide 43.8 to both sides. So we'll just go ahead and do that. And our pressure is going to be 8151.47 divided by 43.8, and our answer is going to be 186.012. So our pressure is 186.12, and that's how you solve a simple PV equals nRT formula. And in this was a example that wanted you to calculate pressure, but in other cases they might ask you to calculate volume or moles or temperature, but not constant because it stays the same. And that's how you solve a simple PV equals nRT formula.